Okay. Okay, hello everyone. Happy New Year to everyone. I hope the semester or the new year is off to a good start. And we're very pleased to have Dr. BJ Fulton with us as the TEPS seminar speaker for today. I've known BJ for a while as we both interacted at Caltech. BJ is an amazing observer in exoplanets. I'm sure many of us know his name, at least from the Fulton gap or the radius gap. And many of his work really revolutionizes our field and really keeps our field going. So BJ started his obtained his bachelor's degree in physics with a minor in astronomy and planetary science from UC Santa Barbara, then went on to University of Hawaii, Manoa for his PhD in astronomy. And then he moved on to Caltech as a Texaco Fellow. And since April 2018, he's been research scientist at the NASA Exoplanet Science Institute, which is also affiliated with Caltech as well as JPL. And I'm very excited to learn more about what he does. He is an award-winning scientist already, like in his early career, earning the one of the top awards for his PhD work. And please take it away.
All right, let me just get my sharing started here. And if I can, I'd also like to get the little laser pointer ready. That's not quite what I wanted. Spotlight, there we go. Okay, can you see the little laser pointer as well? Okay, good. All right, so yes, thank you for the introduction, Eve. It's very nice to be here virtually. I wish I could be there in person, but maybe someday in the future. So I'm going to talk about exoplanet demographics in a holistic view, and I primarily want to focus on this question of whether our solar system is unique or not in the context of exoplanetary systems. So in order to start this story, I need to go to the next slide. Can't have that open. There we go. So in order to start the story, we kind of need to understand the canonical story of how we think the formation of the solar system happened, at least how we learn it in textbooks. So about 4.5 billion years ago, a diffuse cloud of interstellar gas started to collapse into a protostar. Thanks to conservation of angular momentum, that collapsed into a disk-like shape and formed a protoplanetary disk around the young protostar. We think that the giant planets formed out of this protoplanetary disk first in something like 10 million years. And then the terrestrial planets took a little bit longer to form, probably closer to 100 million years to form. The orbits of the planets then interacted dynamically over a much longer time scale to form the solar system that we have today. And this solar system, or this story, held up pretty well for the solar system. We've observed molecular clouds and protoplanetary disks in other systems. We know that gas in these disks goes away at about 10 million years, so those gas giants must form quicker than that. There's geochemical evidence that the Earth is about 100 million years younger than the sun. And then finally, we see evidence of this heavy bombardment period where there was a lot of dynamical interactions going on in the solar system that left a lot of craters on the moon, for example. But this is a good story for the solar system, but we don't know if this really applies generally throughout the galaxy, or if this is sort of a one-off story that works in our system. And with a sample size of 1, we're not going to understand that, and we really need to push this towards exoplanetary systems. So I wanted to focus on these 2 key questions in this talk: whether or not the solar system is typical, and does this solar system formation story that I just went over look like it holds for exoplanetary systems? I'm gonna do this in a little bit of a different order. I'm gonna start with the points that I think I'd like you to take away from this talk, and then try to convince you of these as we go along. So I'm going to go out and say that I think most exoplanetary systems do not look like our solar systems, and I'll explain why. I'm going to show that small planets tend to come in one of two sizes and not in a smooth continuum of planet sizes. It looks like planet formation is highly dependent on the environment in which those planets form, which is maybe not surprising, but I'll show you the details. And then I'm going to try to convince you that Jupiter looks to be maybe a bit unusual, but Saturn is really an outlier. And the combination of both of them makes it even more unusual for our solar system. So let's start with this first question. And in order to answer this, let's first look at some of the general properties of our solar system today. So first of all, it's relatively ordered. We see small planets in a collection close into their star. They're all sort of similar in size and composition. We see an asteroid belt that then separates a similar grouping of giant planets farther out, a little bit more widely separated, but all quite gaseous in composition. We see that all these planets are relatively close to the same plane. They're relatively coplanar. It's only about 7-degree inclination change between any of the planets. And they're all in relatively circular orbits. Okay, so with that in mind, let's start looking at the exoplanetary systems that we know about. So of course, as you know, the last few decades have been a huge boom for exoplanetary science, and we've really been able to start to understand the context of our solar system with a lot of other systems in the galaxy. So of course, this is what we knew about back in 1987, just the planets in our solar system. But as we move time along to 1999, 2008, 2012, and then currently today, we know of thousands of exoplanetary systems, mostly thanks to the Kepler mission that discovered these. And we've started to map out this plane, which is a planet radius on the y-axis and orbital distance away from the host star on the x-axis. We can start to see clusters and patterns in this plane that tell us about the exoplanetary population. We see this group up in the upper left. These are the famous hot Jupiters that were the first exoplanets to be discovered. These are Jupiter-sized planets, also mass planets, orbiting very close to their host star with orbital periods of just a few days. And this is a bit of a formation challenge as well that I'm not going to get into too much today. That's a whole separate talk. Down here on the lower left part of this plot are the hot Earths. So these are Earth size and mass planets, but orbiting very close to their host stars again. These ones are many times even closer than the hot Jupiters, orbiting with periods inside 1 day, and likely have a significant molten surface and even things like silicate atmospheres. In the upper right and outer regions of this plot are where the direct imaging planets live. These are the only ones that we can actually directly see the light coming from them in either reflected light or infrared light. And these ones are very massive, very far out, and they look quite a bit different than the rest of the population. And they perhaps may form in a different mechanism. For this talk, I'm primarily going to be, at least at the start of the talk, I'm going to focus on these small planets where the vast majority of the planets that we know about have been discovered thanks to the Kepler mission. Now, these planets are generally between the size and mass of Earth and Neptune, but they're orbiting relatively close to their star inside the orbit of Mercury and Venus. And since we have no equivalent example of such a planet in our solar system, it's been a long-standing question to try to understand what these planets look like. We'd like to understand whether these things look more like scaled up versions of Earth or more like scaled down versions of Neptune. Do they have a rocky surface with thin atmosphere, or a small rocky core maybe surrounded by a large gaseous envelope? And we can try to understand this, try to answer this question from a few different angles. We can try to come up with models of their formation and try to understand and enter the input physics and try to understand what these planets would look like given the physics that we understand about planet formation. And of course, people like Eve are working on this adamantly. We could try to look at their atmospheres, whether they have thick or thin atmospheres, water in the atmosphere, clouds, and eventually, ultimately, look for biosignatures. I think that this avenue is quite promising in the future. Right now, people like Nick and Bjorn are looking at individual systems and trying to measure the compositions of their atmospheres. We're able to do this, in a few best case scenarios right now. But in the near future, with James Webb JWST and other upcoming missions, I think we're going to be able to start looking at these as a population and trying to get into the field of exoplanetary atmospheric demographics. And I'm really excited about that. But for now, I'm going to be focusing on mostly what we can learn from their bulk properties. So just by learning about their radius and mass, we can get the density, and that already can likely tell us whether these things are rocky or gaseous, just based on their bulk density. Of course, we get the radius from the transit technique, and since most of these were discovered by Kepler, we have the radii of most of these planets, or at least the amount of light that's blocked by this planet relative to the host star. And that amount of light, or the depth of the transit, corresponds to the radius ratio of the planet to the star squared. These are very small signals, but with space-based instruments like Kepler, we're able to pick these up. But we want to be able to turn this into a planet occurrence measurement, understanding the underlying population of planets, and remove selection effects and detection biases from the sample of planets. So I put back up this plane of planet radius versus orbital distance. And I wanted to point out that there's this large gap in the lower right section of this plot, which is something that is not due to the underlying population of planets, but instead due to our detection biases. Those are the most difficult planets to detect, the ones orbiting far away and have small sizes. We miss planets in several different ways, at least with the Kepler telescope. First of all, it requires a very specific geometrical orientation for that planet to pass right in front of the host star. And so it's possible that that orientation is just not right. That's just the transit probability, and that is something that we can calculate analytically. The other way we miss planets is that the signal is simply too small. The planet to star radius ratio are too small, and we can't pick up that signal over the photon noise or even stellar astrophysical noise of the host star. So in order to correct for these effects, the way I have been doing it, at least for this first work I'll talk about, is by calculating these WI terms, these weights. So each detected planet gets counted as essentially more than one planet due to how likely it was to detect that planet. So those weights are just 1 over the probability of detection. This is this issue of signal being too small, times the probability of transit, which is just the geometrical probability. Like I said, the geometrical probability is an analytical term that we can easily calculate, but the probability of detection is something that's much more difficult to characterize. It depends on the instrument and the pipeline used to detect them. And we characterize this by injecting synthetic signals into the data and trying to determine which ones we can detect. So then once we have these terms, the number of planets per star in a region of this parameter space is then 1 over the total number of stars that was observed by the telescope times the sum of these weights. So again, if there's a planet that we detect that's very easy to detect, it'll just get counted as 1. However, if we detect a planet that's in this very difficult area to detect planets, it gets a boost essentially saying there's probably a lot more planets like this that we wouldn't have been able to see simply because our pipeline isn't sensitive enough or the transit probability is too low. So this planet occurrence measurement has been the focus of this field of exoplanetary demographics, of course, for quite some time. And we've learned a lot of things over the years. One of the first results that actually came from rate of velocity work and looking at the planet masses was that small planets, those with masses and radii smaller than Neptune, are incredibly common, occurring around half of all stars that we observe. We see at least one of these planets. Now, I think that the presence of these planets, these intermediate sized planets between the orbit or between the size of Earth and Neptune, and the fact that they almost entirely orbit inside the orbit of Mercury already gives us a pretty good indication that our solar system is not the norm. Now, it's difficult to detect a system like our solar system with the Kepler Space Telescope and any existing technology. But just the fact that we do detect so many of these inner super-Earths or sub-Neptunes, and we don't have an example of that in our solar system, already makes our solar system look a bit unusual. Now, if we go back to the exoplanet demographic work and trying to measure this occurrence, like I said, we understood quite early on that these small planets were very common and about an order of magnitude more common than their gas giant counterparts. However, we were limited by the fact that we only knew the planet radii as well as we knew the stellar radii. And the Kepler telescope observed a lot of faint, distant stars where we didn't have great characterization on those stellar properties, on the stellar radii. So any features that we could observe in these plots of number of planets per star as a function of planet size would be blurred out by this uncertainty in the stellar radii. You could make these bins smaller, but it doesn't really matter because any planet could jump around between them and simply due to the radius uncertainties. So this motivated the California-Kepler Survey, which is a large program led by people all over the country. In all, we had about 50 Keck nights and collected about 2,000 spectra of 1,305 planet hosting stars. We observed, this was a large program with a lot of people involved, and we observed stars for a few different samples. I'm going to be focused on the magnitude limited part of the sample since that has selection biases that we understand. So how did this affect our understanding of the stellar radii? Well, we were able to improve all of the stellar parameters. Before this California-Kepler survey, we knew of the T effective of these stars to about 150 Kelvin uncertainty. After this California-Kepler survey, or CKS, we pushed that down to about 60 Kelvin. Surface gravity had a nice improvement as well. But of course, the one we really care about for this work was the stellar radius, where we went from a typical uncertainty of about 40% down to a typical uncertainty of about 10%. So if you go back and make these plots again of number of planets as a function of planet size, this is simply numbers, but it looks very similar to the planet occurrence corrected version of this as well. I said if you make the bin smaller, all the features would be blurred out anyways, and that's what you see here. It's still just, all we see is this rising occurrence towards small planets and not much else interesting. Note the typical uncertainty there in the upper right. However, when we updated the stellar radii and then the resulting planet radii with the California-Kepler survey work, all of a sudden this very interesting feature popped out at about 1.8 times the size of Earth. There's a significant deficit of these planets, and it seems that planets prefer to either exist in about 2.4 times the radius of Earth, or maybe about 1.2 or even smaller times the radius of Earth. And we think that this gap in the planet population actually separates these two classes of planets, those that do look more like scaled up versions of Earth, which I'm going to call super Earths for the rest of the talk, and then those that look more like scaled down versions of Neptune that I'll call sub-Neptunes. Now, there's definitely some caveats with calling them scaled down versions of Neptunes, but I'll get to that in a second. The presence of this gap is not the only line of evidence that suggests that this is the dividing line between these two classes of planets. If you go out and actually look at the planets where we can measure both the mass and the radius and get a density, first of all, there's a ton of scatter because these Kepler systems are faint and it's difficult to make these measurements for these stars. But if you squint hard enough, you can kind of see that the red points to the left of the gap are on average higher density, where the density axis is on the right side there. And then to the right side of the gap in the cyan color there, the densities are typically on average much lower. Now, this is with the Kepler sample of stars these density measurements have been revisited again with K2 and now with TEPS that we're currently working on. And if you look at these samples of brighter stars, it does indeed look like there is this bifurcation in density space as well. There's these two clear distinct group of higher density super Earths that are smaller and these slightly larger sub-Neptunes that have lower density. Another line of evidence that you can use to support this idea is that if you look at the distribution of these ultra short period planets. Now, these are these rocky hot Earths that I mentioned earlier that are orbiting with periods inside one day. Since they're so close to their host star, we know that essentially that they can't have any significant atmospheres. No hydrogen helium envelope could survive the intense radiation that close to their host stars. So we know that this must be a population of just the rocky cores. We look at the distribution of planet sizes there, and that seems to follow just the left side of the distribution of planets overall. They tail off at about 1.7 times the radius of Earth, and we see very few or little to no planets larger than that on these ultra short period orbits. So that, I think, gives us good evidence that these small planets tend to come in these two sizes, and I think that these two sizes are showing us the two separate classes of these sort of rocky scaled up versions of Earth, super Earths, and then these more gaseous scaled down versions of Neptune. Now, at the time we did this original work in 2017, we thought that we were still limited by the radii uncertainty. That 10% wasn't quite as good as the precision we could get from the Kepler telescope. And so we were thinking that we were still limited by those radii uncertainties. When we tried to fit this population and remove the effect of the remaining stellar radius uncertainties, our hypothesis was that this gap was actually narrower and deeper than we could observe at the time. And in fact, it was possible that essentially no planets exist in that gap. So we were quite excited and prepared for the Gaia data release 2 to come out because we knew that with Gaia, we could improve the stellar radii even further and do this exercise again by increasing our precision by another factor of 4 over what we just did. So the way this works with Gaia is simply Stefan Boltzmann's law, essentially. We know that the luminosity is related to the radius squared and T effective. We can rearrange that to solve for the radius. And then there's the bolometric luminosity term, and there's the T effective to the 4th power. So it's obviously a strong function of T effective, but we have that measured quite precisely from spectroscopy. To get the bolometric luminosity, we can break that down into a bolometric magnitude, as I've done on the bottom here. And in order to calculate that, we need a single apparent magnitude, which is easy enough to measure. We need the extinction in that apparent magnitude band. And if we choose that wisely, that extinction can be essentially negligible at the distance to the Kepler field. We have distance modulus, and this is where Gaia came in. Gaia has given us parallaxes to billions of stars in the galaxy. And so now we have this distance modulus. And then a bolometric correction term that we get from stellar atmosphere models. So how did this improve our results again? So on the left, I'm showing the fractional stellar radius uncertainty. So in the light gray is with the original CKS results, where our median stellar radius uncertainty was about 11%. And with this update, we're able to push that all the way down to about 2%. So for these stars that are, 300 parsecs away or more, we're able to pin down the radius of these stars to about 2% simply with spectroscopy and the parallax from Gaia, which is pretty amazing precision. On the right is the improvement that we saw in the fractional planet radius uncertainty, which went from 13% down to 5%. So we did get about a factor of 3 improvement in the stellar radii relative to the last work. So we're expecting an equally amazing result to pop out of the radius distribution. So again, this is what it looked like before Gaia. And then this is what it looked like after Gaia. And you might notice, I'll flip back and forth a few times, that the difference is not quite as striking as it was the first time we did this exercise. And indeed, we're actually quite surprised to find that the distribution is essentially identical, whether or not we have this increased stellar radius precision. So it did clean up a bit if you look at this distribution in a two-dimensional sense. So now I'm plotting planet size on the y-axis and stellar light intensity relative to Earth on the x-axis here. The color scale is the relative occurrence of these planets corrected for the selection biases. And then the points are the individual planets. Note the typical uncertainty in the upper left. So with the CKS only data set on the left versus the CKS plus Gaia, you're able to see in this two-dimensional sense that these populations do bifurcate a little bit more cleanly than just with CKS. Now that I have this view of the distribution up, I'll go ahead and point out some of the interesting features here. So in the upper left is this notable void of planets. This is known as the photoevaporation desert and was something that has been known about for a while. What's going on here is basically that it's hard for any planets that have any significant envelope to hang on to those envelopes and retain those large sizes. Any planets that would have initially existed up in that region essentially get evaporated away into smaller sizes and go straight vertically down in this plot. And then we see the radius gap that separates these two populations. You might notice that that radius gap is not exactly horizontal. And that contributes to the fact that we couldn't see any sharpening up of the distribution when we improve the stellar radii. We're actually limited by this slope when we look at it in a one-dimensional sense. Since we were able to clean this up a little bit and get higher precision, we're able to start teasing out evidence of stellar mass dependence of the population here. And so I broke up the sample into 3 stellar mass bins that I've labeled on the top 3 plots on the bottom here. You'll notice that the left side is just less than 0.97 solar masses, and the rightmost plot is just greater than 1.1 solar masses. So our leverage is very limited here. We would really like to extend that leverage, and that is ongoing work. But for now, we were able to pull out tentative evidence that the location of this gap between the two populations and the typical sizes of the planets around those gaps tend to go towards larger sizes as you get towards more massive stars. Now, the caveat here is that stellar mass is correlated with both metallicity and age, just due to galactic evolution. And so in this work, we didn't really stick our necks out and say that we know that this is a mass dependence. It could also be metallicity or age. Another way to look at this is simply by plotting the planet size as a function of stellar mass. And you do indeed see that location of that gap seems to increase monotonically, as well as the location of those two populations of planets on either side. Okay, so now that I've talked about the gap and shown you what it is, I wanted to try to come up with some plausible explanations for this, for the presence of this gap. By no means an exhaustive explanation, but it gives some idea of the most popular ideas. So probably the most popular idea is the idea of photoevaporation. So these planets are all orbiting inside the orbit of Mercury for at least the vast majority of them. They're all inside an orbit of 150 days. So it actually goes out close to the orbit of, Venus. And orbiting that close to the stars means that these things are irradiated quite strongly by extreme ultraviolet photons, and especially in the earlier periods of their lives when the stars are much more active. So if we start with a cartoon example of what a planet would look like if it had a 3 Earth mass core and a 20% hydrogen helium envelope around that, well, such a planet like that is going to have a radius of about 4 times the size of Earth. And it also has quite a large cross section. So if that's close to its star in the early days, it's going to be evaporated away quite quickly, down to a point where it reaches a few percent by mass hydrogen-helium envelope. At this point, the atmosphere's cross-sectional area is small enough, yet the gravity of the core is strong enough that it can hold on to this remaining atmosphere, and it reaches this equilibrium point where this few percent by mass hydrogen-helium envelope is the most difficult and takes the longest to evaporate. And so we see planets pile up with this few percent by mass hydrogen-helium envelope. If you started with a slightly smaller hydrogen-helium envelope, so this planet formed with only a 0.3 envelope by mass, that would fall right in the middle of the gap here at about 1.8 times the size of Earth. But that small tenuous atmosphere is going to get evaporated away within the time scale where the star is producing a lot of these XUV photons, and you'll be left with just the bare rocky core, which then has a size of about 1.2 times the radius of Earth. So what this means from a population standpoint is that if you start with a population of planets, like we do in this model here I'm plotting on the left, and you spray essentially a random distribution of hydrogen-helium envelopes on top of rocky cores with some distribution of core masses and sizes as well, this photoevaporation is going to tend to herd this group of planets into these two groups. So you'll see the ones that started initially large tend to evolve downward in this plot, but they pile up at around 2.5 times the radius of Earth. Any planet that gets close to this gap, you'll notice quickly rains down across that gap, play this a few times, and then piles up in this population of bare rocky cores where there's no more evolution because they have no more atmospheres to speak of at that point. So this idea was something that was predicted with models in theory before our observations. And you can see on the left here, I'm again plotting my two-dimensional distribution versus the model distribution on the lower left here. And the agreement is amazingly good with the observations. Since this agreement is so good, we're actually able to pull out some significant implications for planet formation based on the presence and the location of this gap in the radius distribution. One thing that tells us is that these cores, the cores of these planets are essentially water poor. By that, I mean probably around less than 20 to 30% by mass water. And that is simply due to the location of this gap. So that sweet spot of the 3% hydrogen helium by mass, that sweet spot will change based on the equation of state of those cores and the surface gravity of the top of those cores. So if they're less dense with a lot of water, that will tend to shift that gap to larger or smaller radius. The location we observe it essentially indicates that these cores are likely to be an almost Earth-like composition. Some mixture of iron and silicates best match the observation. The lack of a lot of water in these cores probably means that large-scale migration from out beyond the ice line, at least after the first 100 million years, is uncommon. Otherwise, we'd see a lot of cores with much lower density. And it would either blur out this gap so we don't see it entirely, or it would shift it to different spots. Now, there's several other explanations for the gap. You can produce a gap in the radius distribution through impacts on the atmosphere, either from accreting a large amount of pebbles, or a few giant impacts. You can even do this by outgassing. So if these things all started out as rocky cores, you could even outgas a few percent by mass various volatiles. But probably the most popular competing theory is the core heating idea. The idea here is simply that the cores have some heat left over from their formation. That heat has to go somewhere, and it's going to go into the atmosphere and heat the atmosphere, which will then drive atmospheric escape. Now, the observational evidence for core heating and photoevaporation, they look very similar, and either idea can essentially match the observations very well. So any of these could be at work, or any combination of them could be at work. What I wanted to focus on is that there's a quite common thread here, and that's that you have to form these planets out of rocky components. Looks like some mixture of silicates and iron. You have to form the cores of these rocky planets fast enough that there's still gas around in the disk, at least some gas. Accrete that gas onto these young planets, add heat into that atmosphere. That heat can come from internal sources or external sources or impacts or photoevaporation or whatever. But that heat essentially drives atmospheric escape in slightly different ways. And that atmospheric escape herds these planets into these two classes of sub-Neptunes with large envelopes of hydrogen and helium on top of rocky cores, which does look a little bit different than our Neptune in our solar system, but they're similar in size and have a large envelope. And that separates them from the super Earths that have little or no atmosphere to speak of. So I think that gives some evidence that planet formation is dependent on environment. It's clearly sculpted by atmospheric evaporation for the bulk of these planets that we know about from Kepler. And it looks like any large-scale migration probably happens within the first 100 million years, if it happens at all. Okay, so far I've only looked at the very innermost region of the protoplanetary disk. I've been talking about planets that all orbit, around the orbit of Venus and inside. But there's a lot more going on in our solar system, and we'd like to understand that for exoplanetary systems as well. So the next thing I've been looking at is the frequency of long period gas giant planets. And this has been a study for quite some time. It was a measurement that was accessible to much lower precision instruments, but you need a long baseline. You need to observe these stars for a long period of time in order to map out orbits in the outer regions of the exoplanetary systems. So some of these early works, one of the most seminal is by Cumming et al. In 2008, in which he measured that the frequency of giant planets orbiting solar type stars is significantly enhanced around 1 AU. Again, this was something that was predicted by planet formation theory. And if you looked at, if you made these models of planetary formation and input the physics and just tried to form planets, you do indeed see that there's a concentration of these giant planets out around 1 AU. And the idea here is that the ice line in the protoplanetary disk is likely important to augment the formation of these gas giant planets. Those additional solids in the protoplanetary disk help to form the cores faster when there's more gas around in those disks, and then they can run away and become these gas giants. But we'd like to understand what happens beyond this 1 AU limit that was reached by Cumming et al. Simply due to the extent of their data. We'd also like to understand if we still see this enhancement around 1 AU for lower mass planets, Neptune and Saturn's. And this is important for a variety of reasons, just to understand the basic physics of planet formation, but also direct imaging surveys need this information to predict their yield, especially these large future direct imaging missions based in space, like the Roman Space Telescope. And they're also going to need targets to go observe. It's too expensive to just blindly survey the whole sky. So we'd like to identify some of the best targets to image in radial velocity work instead. So I just hinted this work has been done with radial velocity data, and we're calling this work the California Legacy Survey. Most of the data comes from Keck Observatory, where most of these stars have been monitored since about 1994. One of the great things about the high-res instrument on the Keck telescope is that it has been fiddled with very little. There's one disruptive upgrade in 2004, but otherwise the instrument hasn't really been touched, and we can be sure that these long-term trends we see in the data are not due to fiddling with the instrument over the years, but actually astrophysical in nature. Some targets in our data set even have Lick Observatory data going all the way back to 1988. So we have 30 years of baseline in some cases. So this work has been driven, of course, by detecting these planets in radial velocity data. And This has been thanks to work done by a graduate student who's working with me, Lee Rosenthal. He's developed this RV search package, which is based on another tool that I developed called radial, in which we simply try to fit Keplerian models in a bunch of different combinations to try to see which ones are a better fit than the null hypothesis. With that, we're able to discover a few dozen new planets and, importantly, redetect all of the known planets orbiting these stars with this pipeline, so that we can then characterize it using injection recovery tests, just like was done with the Kepler occurrence work. So you might wonder, how we can detect planets out, at 15 AU when we have these 30-year baselines. Well, the detections look something like this in these outer regions. This is one example of a system that was published by Sarah Blunt a couple years ago. This is a highly eccentric system, and we were just passing through periastron passage in the last few years. Since the orbit is changing so quickly during that time, or the acceleration is changing so quickly, we're able to constrain this orbit quite strongly with just a limited part of the orbit. And of course, there's other systems in our sample as well that look similar. This one happened to pass periastron passage long time in the past, and now it's sort of in the boring part of the orbit. There's also new planets down here around 1 AU that have lower masses than have been able to that we've been able to access before, simply because we have so many orbits of these planets now. We're able to pull them out very significantly. So in all this study, we have about 721 stars with baselines of at least 16 years and at least 20 observations, so we can search for planets. And probably the most important thing is that we've been very careful to try to assemble the sample such that we understand why these stars were observed, and that they were observed for blindly searching for planets. It was not the case that they were followed up because we knew of a transiting planet there, or someone else published a planet system there and we wanted to characterize it ourselves, or it was part of some survey where we targeted metal-rich stars, for example, because we knew there's more hot Jupiter planets there and we wanted to detect more planets. So we tried to make this as clean of a statistical sample as possible by by making a conglomeration of a bunch of historical surveys in the best possible way. With all of these stars and these large baselines of radial velocity data, in all we have about 102,000 radial velocities and 161 days of open shutter time, primarily on high res, which if you are a radial velocity specialist, this is an unprecedented amount of radial velocity data in a single survey. Okay, so I'm going to skip over the complicated work of turning that into occurrence and stuff that we talked about before and jump straight to the results here. So now I'm plotting number of planets per 100 stars, and it's corrected per delta semi-major axis bin. So it's a rate per semi-major axis a decade. And we're looking at masses of planets now as opposed to radii, limiting ourselves to 0.1 to 20 Jupiter masses, or 30 to 6,000 Earth masses. And I'm plotting versus semi-major axis on the x-axis. The dashed blue is the raw counts of planets, and then the thicker black line with uncertainties is then corrected for the planet occurrence things that we talked about before. Now, some of you may have seen me give, or show this plot before, or similar versions of this plot before at other conferences. And it's evolved significantly over the past few months, actually. We've been able to greatly improve our occurrence and measurement techniques by incorporating hierarchical Bayes techniques and all of the sources of uncertainty we can think of. And what's happened is that our uncertainties have been inflated. And what we thought we could say that there was a significant fall off in planet occurrence just beyond 3 AU, now is much less certain. It actually looks like it is compatible with being flat out beyond that. We do see the enhancement around 1 to 3 AU. It does seem to extend out to at least 5 AU, but it's difficult to say what's going on beyond that. Now, this has been the study of a few recent works. a couple of which are Fernandez et al. 2019 and Whitmire et al. 2020. Both of, well, Fernandez et al. Made this measurement using archival HARPS data, and they essentially fit the distribution, assuming a power law or a broken power law distribution, and suggested that there was a significant fall off just beyond about 3AU in the occurrence of these planets. Now, I'll say that our evidence tends to agree with this, but the uncertainties are much larger. And the primary reason for this is that we've pushed our survey out to much larger separations, and we're incorporating smaller portions of an orbit. And with our injection recovery tests, I think we're able to characterize our completeness out at those outer regions for those partial orbits much better and more appropriately estimate our uncertainties. Whitmire et al. 2020 also attempted to make this measurement, and you see that they have quite large uncertainties here in this magenta line. They're not able to push quite as far out as us, but they generally agree with the overall occurrence rates. Now, in green here is our attempt to model this distribution with a broken power law, as opposed to just a series of bins with constant occurrence. And we do see that it looks like the evidence suggests that the occurrence falls off quite drastically past 3AU, but it depends on on the model you choose. If you assume a broken power law, you'll see a broken power law in the data, and it does look like it falls off. But trying to directly measure it as a series of bins with constant occurrence within them, it's not quite so clear. Another thing that we wanted to look at, I mentioned earlier, was whether or not we see this same effect, this enhancement around the ice line for the slightly smaller planets. And so that's what I'm plotting here. So instead of the semi-major axis on the x-axis, this is mass, or m sin I now. And down to the limit of what we can detect and characterize well, it looks like these planets that are orbiting farther out at 1 to 5 AU, plotted in blue here, are more common for all masses. So all the way down to about 30 Earth masses, or about the mass of Neptune, these planets are more common farther out than they are closer in. Another way to look at this is simply to break up these two samples and again plot it as a function of semi-major axis, where we see this large enhancement in both the green and blue lines that correspond to the super-Jovians and the sub-Jovians. But again, it's not quite clear what's going on beyond that at 10 to 30 AU. So let's bring this plot back up and try to tie it back into the context of our solar system. So Jupiter is out here at about 5 AU. Now, we don't have a ton of planets detected. You see the raw count, so it's only about 4. We don't have a ton of, well, 4 per AU bin, sorry. We don't have a lot of these planets, but they do appear to be near the peak of the distribution, if not quite a little bit farther out. However, Saturn, it does appear to be, is pushing out towards the region of occurrence where our evidence suggests that these planets are much more rare. Really though, what makes it unusual is that we have 2 of these giant planets that are in nearly circular orbits. So first of all, about half of the cold Jupiters that we see out in that population grouped around where we see our Jupiter, about half of those are highly eccentric, whereas Jupiter is on a nearly circular orbit. If you ask how many exoplanetary systems have 2 giant planets between 1 to 10 AU, it's only about 4%. So it's very rare to have 2 giant planets so close to each other in that region. And then you ask the question, how many have 2 circular gas giant planets? Well, there's 1 in our sample that looks like it is similar in that sense. So it's really rare to have, it's not necessarily rare to have one planet that looks like Jupiter in these systems, but it's very rare to have 2 planets that look like Jupiter within 1 to 10 AU, both on circular orbits. That, I think, makes Jupiter and Saturn, especially their combination, a bit of an outlier, because most giant planets have these, most systems have giant planets between 1 to 3 AU, and their orbits are eccentric. Okay, so I wanted to finish up by going back to the formation of our solar system story. and see how it's held up for the population of exoplanetary systems that we've discussed. Well, so far the evidence for the first few processes seems to hold up. We see these diffuse interstellar gas clouds, like I mentioned earlier. We see protostars and protoplanetary disks. We have direct images of them from Hubble. The giant planets still probably form first, followed by terrestrial planets, but it seems like the terrestrial planets probably need to form a bit faster than that 100 million year timescale. They need to form fast enough that photoevaporation is still happening, and that happens primarily in that first 100 million years. In addition, they need to form when there's at least still a little bit of gas left in that protoplanetary disk, and that seems to go away in about 10 million years. So somewhere between a few million years and a few dozens of millions of years is when the terrestrial planets likely form in most exoplanetary systems. In addition, I think we need to add a step here, and that's atmospheric sculpting. Clearly, it's an important part of the planet formation story for the vast majority of planets that we know about so far. And then dynamical interactions are indeed important, it appears, in these exoplanetary systems. There are lines of evidence that I didn't get into in this talk, but it looks like dynamical interactions are indeed important in the majority of exoplanetary systems, but perhaps not in the same massive scale that we saw in our solar system. The Grand TAC model, for example, has Saturn and Jupiter migrating across large distances in the solar system, pushing water-rich material to the inner planet or the inner planets. It doesn't look like this is the norm based on the composition of the cores for exoplanetary systems. And with that, I think I'm out of time. I'll go ahead and leave up my summary slides with the key results and take any questions you might have. Thanks.
Okay, thanks, BJ, and I'll clap for everyone else since we're in a virtual environment. Questions?
Can I ask a question, or do you want me to raise my hand?
No, go ahead.
Okay. Thank you, BJ. That was a really cool talk. So for the stuff you're talking about at the end with the long period planets, do you get a cleaner behavior around 1AU, around the maybe where the snow line would be, if instead of plotting semi-major axis, you plot something that more directly relates to the snow line, like the luminosity of the star or the expected luminosity of the star at some point in the past or anything like that?
The one thing I've tried is plotting is insolation flux or stellar light intensity relative to Earth, like I've made for those other plots. And surprisingly, no, it actually looks to be a smoothly increasing function. You don't actually even see this step function at 1AU. It's much more smooth. And so no, I was surprised to see that it's still just as broad around 1 to 3 AU.
So does that give you a hint of what it might be related to? Does that mean that it's not related to an ice line, and maybe it's some weird?
I don't know. It's probably just blurred due to small migrations or dynamical interactions in later time periods of these systems. That's my theory, but I don't really know.
I have 2 questions, if that's okay. So I've worked on long period planet occurrence with transit data, and one of the biggest issues is sometimes you get false positives from binary stars eclipsing. So does radial velocity have anything similar in terms of false positives that affect your results?
Yeah, it's definitely a bit easier to weed out many of the false positives. So eclipsing binary stars will often have 2 sets of stellar lines in their spectra. And so we can easily remove those from our sample. In fact, we can't even do good radial velocities on those stars anyways. So one of the first indications is that our pipelines fail and we don't get good radial velocities. And then we go look carefully and we see 2 sets of lines as the reason why. In addition, we're reaching out to the outer regions of the disk where it's quite possible to image any companions that would be out there, even brown dwarfs. And these stars have been surveyed for the vast majority by AO surveys, direct imaging surveys in the past. If not really high precision direct imaging surveys, they've at least been looked at by things like RoboAO. So we have a pretty good idea that we don't have binary stars. Well, we do actually. We see a lot of radial velocity accelerations due to binary stars. But those are not included in the occurrence analysis. We're able to weed them out and separate them quite easily.
Right, cool.
The big false positive that we do have to worry about, though, is magnetic activity cycles of stars. They tend to look just like, so this is like the 11-year solar cycle of our sun. As you get more and less mean numbers of spots on the surface, that changes the mean radial velocity just a little bit as well. And that looks just like the signal of a Jupiter type planet. So those are the trickiest false positives to weed out, but we have some other metrics in the spectrum that we can look at to disentangle it.
That's cool, thank you. My other question, if you don't mind, is have you looked at anything related to like planet multiplicity or the relationship between inner planets and outer planets? I know your sample is mostly not stars that have been observed before to search for planets, but can you comment on that at all?
That is work in progress. So Lee Rosenthal, who developed the search pipeline, is now working on a series of follow-up papers in a flurry. So this initial measurement of the semi-major axis distribution, I am about ready to submit. There's shortly going to be 2 papers coming after that. One is looking at the eccentricity and metallicity distribution. I gave some teaser plots from that. The other one is looking at the influence of inner companions to outer companions. I don't really have anything to show from that. It's really early work, but it will be coming out in the next probably year or so.
Cool, I will look out for it.
Yeah.
We have time for one question. Well, let me ask one very quick question. You may have told me this when we were at Caltech, but could you like go over, so like my understanding from the radius gap as detected using the astroseismology sample is that their gap is much more empty. It's almost like completely empty. Like, is it just like the difference between that and CKS? Is it just due to the different stars, or is there something more than that?
Yeah, so we think what's going on there is that the distribution of stellar masses is rather narrow for that sample, the astroseismic sample. And I showed one plot where if you break up the sample in groups of stellar mass, it cleans up the distribution a bit. So some of the filling in of the gap actually has to do with overlapping samples in mass. In fact, this upper right plot, you can see that if you squish it horizontally, it's going to fill in that gap a little bit. You have to squish it at an angle, right? So that I think has something to do with it. There is new work that's under review right now by Trevor David, looking at very young stars, and that evidence seems to actually suggest that's not necessarily the case. There's probably stars or planets that fill in the gap at all ages and all masses. It's not totally empty in any bin. But yeah, if you break it up by stellar mass, it just cleans it up a little bit. And then combined with the smaller sample size of the astrometric sample, essentially looks like there was just luck that there was no planets in the gap for that sample. Yeah, so there's still a little bit of ongoing discussion, I think, about what's going on there.
Okay, cool. And we're at the hour. So thank you again, BJ. And thank you, everyone.
Thank you for inviting me.
Yep. Bye.
Bye.